lecture, which is about the CPU scheduling. So, as you remember, I introduced 6 algorithms, scheduling algorithm: first come, first serve, shortest job, and shortest job first, priority, round robin, multi-level algorithms. Today, and in this video, I will explain you the first 2, first come, first serve, and shortest job first schedule. So let's start with the first come, first serve. So first come, first serve, as you can understand from the name, the first process which comes will get the CPU time and be executed. So the process that requests the CPU first is allocated the CPU first. First come, first serve. And it works based on FIFO, first in, first out. So look, the first one who comes sits at the first, on the head of the queue. The next one comes like 2, goes here, third, 3, 4, 5, and the last one. When you want to execute them, you execute from the head. The first one is executed, then second, third, fourth, and fifth, and sixth at the end. So this is first in, first out. So the first process who comes and gets the CPU will be executed and go out, and the next one, and next, and next, and next. So this is how this algorithm works. When a process enters the ready queue, its PCB is linked onto the tail of the queue, like as I explained in the FIFO. When the CPU is free, it's allocated to the process at the head of the queue. The running process is then removed from the queue. As I explained, the first one comes, gets a CPU, and execute it, go out, and the next. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU, either by terminating or by requesting input-output. If you remember, I explained something very important, which is called non-preemptive scheduling. In non-preemptive scheduling algorithm, we said that interrupt is not handled. When one process comes, it gets the CPU time and executes. The CPU executes that. So it means that it doesn't stop and go out of the CPU and come back again. No. When it goes to CPU, it gets the CPU time and CPU executes that process. So that's a non-preemptive scheduling algorithm. Let me give you an example. With the examples, you can understand better how this algorithm works. So consider the following process that arrive at time 0. As you see, all of them, P1, P2, P3, arrives at time 0 here. Imagine that's a number line. So I'll explain that what it is. All of them comes here. With the length of the CPU burst given in the milliseconds. These are the CPU time, the burst time. How much takes the CPU execute them. So, for example, P1, 24 milliseconds, P2, 3, P3, 3. They arrive in the order P1, P2, and P3. P1, P2, P3. All of them comes at time 0, but with this order. So you can imagine that 3 processes are here. So the first one, because that's first come, first serve, because P1 is the first process, it should be executed first. So the first one comes, it takes 24 seconds. You can draw this and show that it takes 24 seconds to be executed. The second one is P2. How long will it take? 3 seconds. After 24, 24 plus 3, 27. So it gets the CPU from here, second 24. It takes 3 seconds till 27. Execute, terminates, goes out. And the next one, P3, which comes after P2, it takes another 3 seconds and it terminates at second 30. What it is, it's called Gantt chart of the schedule, or this is our schedule for these processes. Very important. Whenever we want to solve a scheduling problem, we must draw this Gantt chart because it helps us. Because drawing the Gantt chart is not important. I told you about some criteria for the schedule algorithm. 2 of them which are very important, I said. One of them is waiting time, and the other one is turnaround time. We've got to calculate. To calculate this, as you see here, this table is very, very helpful and useful. I do recommend you for every single schedule problems, draw the answer, do the table, and answer the questions that you will get. For all these 4 or 5 algorithms that you get numerical problems. So let's see how it is. The arrival time for all of them is 0. The burst time, as you see, 24.33. The next column is exit time. We want to see when they finish. The exit time for the first one is 24. The second one is 27. The third one is 30. 24, 27, 30. What is turnaround time? As you remember, I said that turnaround time is exit time minus arrival time. How much time the process is in CPU. So 24 minus 0, exit time minus arrival time. It arrived in second 0, it goes out in 24. 24 minus 0, 24. The next one, it exits 27, second 22nd, but it arrived in 0. So 27 minus 0 is 27 milliseconds that this process was in the ready queue to be executed. And the last one, 30 minus 0, oops, there is a typo here, I will fix that. It should be 30. 30 minus 0 is 30. Sorry for that. So, what is waiting time? Waiting time is the turnaround time minus burst time. So, the turnaround time for the first one minus the execution time, or sorry, burst time, gives us the waiting time. So, it's obvious. The first one, as soon as it arrived, actually it got executed. So, the waiting was 0 because the exit time was 24, the burst time 24. 24 minus 24 is 0. The second one, the turnaround time is 27, but it took only 3 seconds to be executed. 27 minus these 3 gives us 24, which is the waiting time, which is right, because it waited 24 seconds, as you see here. 27 minus 3 is 24. The last one, the turnaround time is 30. It took 3 seconds to be executed, 27 to wait. 30 minus 3 is 27. If you take the average of these 3, we call it average waiting time. 0 plus 24 plus 27 divided by 3 is 17. Then average turnaround time is 24 plus 27 plus 20. Divided by 3, the average of them for these 3 turnaround time is 23.7 milliseconds. As you see, the turnaround time and waiting time, it's quite high here, as you see, because they took only 6 milliseconds for these two processes, but they had to wait 24 and 27 milliseconds. So it's not an efficient algorithm. But this is the very basic one. Next one, if we change the order of them, let's see what happens. This time, instead of P1, P2, P3, we start with P2, P3, P1. So P2 comes first. All of them arrive in the second 0, but the order is different. P2, P3, P1. So P2, first of all, gets the CPU. It takes 3 seconds. Then P3, another 3 seconds. And at the end, P1, which is 24 seconds, which actually finishes at 30, as you see. 3 seconds, 3 seconds, and 24 seconds. Let's do the calculations for that as well. So we've got the arrival time, we've got the burst time for all of them, but the exit time are different. The exit time for the first one is 30. For the second one is, for the third one, sorry, is 6. For the first one is 3. So the turnaround time is exit time minus arrival time. Exit time 30 minus 0 is 30. So P1 was in the process for 30 seconds in the ready queue and execution time. So 30 seconds. Second one, which is P2 here, it arrived at 0, finishes at 3. So the turnaround time is 3 seconds. 3 minus 0 is 3. The turnaround time for the last one is exit time, which is 6, minus 0, which is 6. That's right, because it is here for 6 seconds, although it waited for 3 seconds that we'll see here. So let's discuss the waiting time. The waiting time is the turnaround time that it you actually calculate here, minus the burst time. It gives you the waiting time. Look, 30 minus 24 is 6. Is right, because look, P1 waited 6 seconds to be executed. The next one, 3 minus 3 for P2, it waited 0 seconds. That's perfect. So the waiting time is 0. And the next one is 6 minus 3, the execution is 3 seconds, which is this waiting time here. As you see, the waiting time for this here is 6 plus 0 plus 3 is 9 divided by 3, which is 3 milliseconds. So just look at this. The average waiting time for this order, the same problem, but we just changed the order of them. The waiting time is 3. For the other one is 17 for the same problem, but we just changed the order. So as you see, if we can change the order of them, you could actually have a better, more efficient machine, an operating system. So it depends on the order in this algorithm. I want to give another example, but this time the arrival time are not 0. They comes in a different time. So as you see here, the arrival time for 4 processes is 0, 2, 4, and 5. And you have the burst time here, 7, 4, 1, 4. So as you see here, the first one comes in second 0, the second one 2, 4, and 5. Because I want to show you how you can draw this Gantt chart. Because P1 arrives at the beginning, so it should be executed. How long it takes? 7 seconds, milliseconds. So because it comes at the beginning, it's first come first served, it should get the CPU. So look, it gets all the 7 seconds here, be executed and go out. This is the exit time. P2 comes after that. How long will it take? 4. 4 plus 7, 11. So this is the exit time for the second one. P3, here. After that, after P2, how long it takes? 1. 11 plus 1, 12. And the last one, P4, 4 seconds. 4. P4, it takes 4 milliseconds. 4 plus 12 is 16. As you see, this is our Gantt chart when the arrival time are different, but it's still the same concept. First come, first served. Let's calculate the average waiting time and turnaround time, or here, only average waiting time. This is our Gantt chart that we drew in the previous slide. So we've got the arrival time, we've got the burst time, 7, 4, 1, and 4. Exit time, you can read it from this Gantt chart, 7, 11, 12, and 16. Turnaround time is exit time minus arrival time. Exit time minus arrival time, 7. 11 minus 2, 9. 12 minus 4, 8. 16 minus 5, 11. These are the turnaround time. Look, 7 seconds. It's because it arrived not in the second 0, it came at 2. So 11 minus 2 is the turnaround time for the second one. The same for this one. 12 minus 4 is 8 seconds it took to be executed. And the last one, as we see. Waiting time. The turnaround time minus the burst time gives you waiting time. Look, 7 minus 7 gives you waiting time. That's right, because as soon as it arrived, it got executed. So it waited 0 seconds. Second one, P2, 9 is the turnaround time, minus 4, the burst time, 5 seconds. So that's right. Look, because it arrived at second 2 here, and it waited 5 seconds, 5 plus 2, 7 to be executed. So the waiting time is 5. So these formulas are quite helpful. And 8 minus 1, which is 7. Here, the waiting time for third one. And the last one, 11 minus 4, which is the waiting time for the P4, which is 7 seconds. That's right, because it got the CPU time from second 12, it arrived at 5, so it waited 7 seconds to be executed. So the average time is 0 plus 5 plus 7 plus 7. If you divide it by the 4, you get 4.75 milliseconds as average waiting time. So a summary of that, it's non-preemptive, first come, first serve, easy to use, but it's not a high-performing algorithm, and the waiting time is quite high in that. But that's the first type of algorithm which was used. So let's move on to the next one, which is shortest job first. It's really good. As you see, it's optimal. It gives you a minimum average waiting time, which is fantastic. How it works? This schedule algorithm, it works based on execution, the shortest one. So it means that whenever you have the queue in front of you, you choose the one who's got the least burst time. So we choose based on the least burst time, and we choose them. But the problem here that it's out of the scope of this is that how to define the process time, but we don't actually touch it here. And what is important is we've got to pick the one who's got the least burst time. I discussed it in two different parts, in non-preemptive and preemptive, and it's important. In non-preemptive, it means that we cannot stop any process. We've got to give the CPU to that process to be executed and finishes that. So let's see. I have 4 processes here, P1, P2, P3, and P4. All of them arrives at time 0. All of them arrives at time 0 here. I've got the burst time, 6, 8, 7, and 3. So all of them, imagine all of them are here, and you want to give CPU time to them. Which one should be executed first? Shortest job first. The shortest. Which one is the shortest? P4. P4 gets the CPU. For how long? 3. It goes for 3. After that, between these 3, between P1, P2, and P3, the remaining process, which one should get the CPU? Yep, P1, because it's the shortest. P1 goes there. It takes 6 seconds till 9. So we don't have P1 and P4 in the ready queue, and we've got to choose between P2 and P3. Which one? Definitely P3, because 7 is less than 8. So we give the CPU to P3. And as you see, P2, which is the longest process, we give the last place to this one. So as you see, 16 plus 8 is 24. This is how we can create a Gantt chart, very easy, for non-preemptive shortest job first scheduling algorithm for these 4 processes. Let's calculate the average waiting time. So we've got this. I'll explain you how to get that. Arrival time, burst time, and exit time. 9 is for the first one, as you see. The exit time for the first. Second one is 24. 24 is second. P3 is 16. 16 is here. Ending time is there. P4 is here. The exit time is 3. Exit time minus arrival time gives us the turnaround time. So if you subtract these 2 columns, you get the turnaround time for the processes. 9 minus 0 is 9. 24 minus 0, 24. 16 minus 0 and 3 minus 0 gives you turnaround time. Waiting time, just take away the burst time from the turnaround time. 9 minus 6 is 3, is right, because P1 waited 3 seconds. Took 6 seconds to be executed. P2, 24 minus 16 is here, which is 8. 24 minus 8 is 16. Sorry, this is the waiting time for that. And the last one, 3 minus 3 is 0, the waiting time for that. So as you see, 3 plus 16 plus 9 plus 4, if you add all of them, find the average of that, it gives you the waiting time. If you do the same, what I want you to do the same, solve this problem, but using first come first serve algorithm, and see what you get. The answer is 10.24. As I said, the shortest job first gives you the best, it gives you the minimum waiting time. So if I want to give an example with different arrival time, but different arrival time and with the burst time, and see what happens. So we've got the arrival time and we've got the burst time. So P1 comes, because it's non-preemptive. As soon as P1 comes, it gets the because there is no other process here at time 0, because we have at time 0 we've got only P1. So P1 will get the CPU and it executes the process for 8 seconds. Now we have 3 processes here. We have P2, P3 and P4 available. Which one should be executed first? We look at the burst time. We choose the shortest one. P2, 4 seconds, 8 plus 4, 12. Next one is P4 between these two, because P1 and P2 executed, these two remaining. Between these two, we give the CPU to P4, 5 seconds, sorry. 17. 5 plus 12, 17. And the last one is P3, which is the longest one, which is 9. 9 plus 17 is 26. This is the Gantt chart for that. So again, the same concept, shortest first, but we've got to look at the ready queue first. How to calculate that? You've got all these values, burst time, exit time. If you subtract by turnaround time, you see, you get the exit time minus arrival time gives you turnaround time, and if you subtract that by the burst time, you get the waiting time for that. If you have this waiting time, and if you find an average of this, you see that the average is 7.75 milliseconds. The formula is here, and this is important. If you can draw the Gantt chart, you can easily make this table and find the answers. So I solved 2 problems for shortest first job using preemptive as non-preemptive with same arrival time and with different arrival time. Now go for a preemptive one. The choice arises when a new process arrives at the ready queue while a previous process is still executing. It means that when a new process comes, it can stop the current running process and say, okay, let me see how long you take to be executed, how long it takes for me to be executed. So it chooses the shortest one. So it means that it can stop the process at any time. The next CPU burst of the newly arrived process may be shorter than what is left to the currently executing process. A preemptive shortest job first algorithm will preempt the currently executing process, whereas a non-preemptive SJF algorithm will allow the currently running process to finish its CPU burst. So let me give you an example. So the example of preemptive shortest job first. It's very important. So we have 4 processes with different arrival time and different burst time. So we've got them. I want to show you how we can create the Gantt chart for that. I'll show you the P1, P2, P3, and P4. This is their arrival time. So the first one comes, it gets the CPU, and it goes until it sees the next process which is coming. So the first one comes, it takes 8 seconds, but when 1 second goes, the next one P2 comes. So 1 second goes from this. The remaining base time for the first one is 7. So here we've got this 7 and P2 arrives, which is 4 seconds. So which one between these two should be executed next? Because you can stop the process at any given time. So here you can stop P1. So look at this point, you stop P1 and you look at the remaining burst time for P1 and the burst time for the P2. Which one is shortest between these two? P2, definitely, because 4 is less than 7. So P2 gets the CPU. 7 times remains for the first process, and second one gets the CPU. So it goes. When it goes, P3 and P4 comes. They can stop P2, but as you see, the burst time for these two processes, P3 and P4, were more than 4 seconds. Because of that, P2 continues, because this is the shortest. For example, at this time, only 3 seconds remains from P2, but P3 is 9 seconds. So CPU scheduler gives P2 the CPU. When it comes here, again, 1 second only remains from P2, but it is 5 seconds. So again, scheduler gives 5 seconds, gives the CPU to P2. So from this point, we see that P2 executed, 0 remains, 7 remains from that, 5 remains from this. Actually, we have 5 for that and 9 for this one. Which one should go next is the P4. P4 is the next process to be executed because that's the shortest process here. So as you see, the next process is P4, 5 seconds till second 10, 5 till 10. The remainder, 0 because it's executed. Next one, we've got to choose between these two. Which one, 7 or 9? Definitely 7. 7 is shorter. So P1 gets a process for 7 times, 10 till 7. And the last one is P3, which is 9. As you see, we executed all of them. We preempt P1. As you see, we started with P1, but P1 finishes at here. Between starting and finishing execution of that, P2 and P4 got CPU time. Because of that, we call it preemptive. We can stop the process and give the CPU time to other. Let's calculate the average waiting time. So as you see, you've got to exit time. This is the exit time for P1. Look guys, 1 is not the exit time because process 1 leaves the CPU at this point. P2 lives here, P3 lives here, and P4 lives here. So as you see, 17, 5, 26, and 10 are the exit times. What are the turnaround times? Just subtract that by their arrival time. So if you subtract them, 7 minus 0, 17, 5 minus 1, 4, 26 minus 2, 24, and the last one, 7. Waiting time, subtract this by their base time. Minus 8, minus 4, and the rest. So you can get the waiting time here, 15 and 2. What is the average? Add all of them. 9 plus 0 plus 15 plus 2 divided by 4 is 6.5. If you go and solve this problem for non-preemptive, you see that the waiting time is 7.75. It means that this algorithm works better than non-preemptive because it tries to minimize the waiting time. So shortest job first for preemptive approach actually gives you a better waiting time. Summary, SJF is preemptive, non-preemptive. It reduces the waiting time. When the CPU is available, the next processor job with the shortest completion time will be executed first. The algorithm method is useful for batch time processing, where waiting for jobs to complete is not critical. And we want to finish something, but very quick. It improves job output by offering shortest job, which should be executed first, which mostly have a shorter turnaround time. So that's the end of this video. Please practice all of these processing scheduling problems, which are very important and you see in your exam. Thank you very much, guys.